Can you hear me? Hello? Hello? Can you all hear me?
Yes.
Okay, so last time we discussed this Cartan killing form, and in this week we will see how powerful is this Cartan killing form, and it will allow us to basically deduce in a completely abstract way. I mean, without really dealing with some explicit matrices, we'll be able to deduce the general properties, and we'll see that it's almost the same. The structure is the same as SU3 structure, all of it. So. It doesn't erase completely. Huh? So 11.1, section 11.1, is it all clear to everyone? Right?
Actually, I was going to ask you, Professor, about something. H1 and lambda 8 are orthonormal, right?
Lambda?
Lambda 8 are orthonormal, but H1 and H2 are not orthogonal.
H1 and H2 were not, yeah.
So P of H1 and H2 is a metric of two not orthogonal bases.
So yeah, exactly. Yeah. That is, in fact, if you look at this exercise, I forgot to bring my specs. The 11.1. What you had to prove was that B, H1, H2 was equal to 2 sum alpha
Alpha equals 1.
H1.
Alpha equals 2.
I goes from 1 to 3. Huh?
For sure. But I was struggling with the two factors.
The two factors. Yeah. Okay, this is because, I mean, there are two ways of writing it. One, to write it without this 2, but then you sum over all the roots, I equal to 1 to 6. You see, for every positive root, there's a negative root, right? So if you, now you can split into, so you have 1, 2, and 3, alpha 1, alpha 2, alpha 3, and then you have minus alpha 1, no? Alpha 1, so for our alpha 1, there is also minus alpha 1. So if you take minus alpha 1 times minus alpha 1, it's again plus sign, no? So you get a factor of 2. I think I noticed that in his notes, many times one just writes it as a sum over all roots, no? Sum over all roots. In that case, you don't have the 2 factor of 2. But now, when we have factor of 2, then we are saying sum over all positive roots.
5 from 1 to 3.
Yeah. So now it's only 1 to 3. Yeah. That's correct.
On the other page, Professor, he defined the H as sigma 3 over 2, and then which is equal to HITR.
So which page? This page here?
Page 76.
Page 76. Huh?
After the note, he said, and then for example, for H is equal to sigma 3 over 2 is equal to minus IT3. HITR. I didn't understand HITR.
HIG, where is it? You mean you are looking at this formula, Bij? Is it that formula you're looking at?
Bij is equal to negative 2 delta ij.
Minus 2 delta, yes.
That's completely clear. The next line. And then, for example, for H equal to?
Sigma 3 by 2.
Exactly, this line. I get confused when he defines H in terms of HI and TI.
HITI. Where, I mean, so in this basis, HI is equal to minus I delta I3. No? So then it's just T3 minus whatever.
It is minus I, right?
Minus IT3, yeah. So one has just written it as a linear combination. So of course H is minus IT3 in this case, but then you just want to rewrite it as some numbers, because anyway it's going to be some linear combination of all the Lie algebra generators, right? This is going to be some linear combination. So it's just written as HITI, where of course H1 and H2 are 0, and H3 is just minus I. That's just a way of writing it. It's just that, I mean, in general, this is going to be some linear combination of all the Lie algebra generators, right? So probably it's not very needed. Is it needed really?
Yes.
Okay. Yeah, really, I mean, it's not so important, right? I mean,
it is not necessary to
yeah,
find it this way.
exactly,
Right?
exactly. Yeah. Because anyway, HI is minus I delta 3I,
Exactly,
so
yes.
it doesn't, it's not needed actually. Yeah. This formula is quite important. This formula. Okay. So in particular, what would it say? B H1H1. Let me just write it down because this I will need later, this information. So B H1H1, do anyone remember? I mean, so for us, I mean, this is general, right? Okay, B H1 H2 is that, but B, in general, B HI Hj will be, oh, again, this I index, I don't know, AB, let's say. AB will be that, right? If I take, I mean, these are the Cartan generators, some Cartan generator. Or more generally, I mean, if I just call B HK, HK, where H and K are in Cartan subalgebra, belong to Cartan subalgebra. Okay. Then this will be simply B of H, alpha I of H, alpha I of K, right? That, no? I mean, this simply comes from the fact that it's not diagonal. In the add H, what you will have? Add H will be 8 by 8 matrix, right? 8 by 8 matrix, where suppose I choose the basis that say the first one is x alpha 1, x alpha 2, x alpha 3, and then the minus one of them, minus x minus alpha 1, x minus alpha 2, x minus alpha 3, and finally the Cartan subalgebra, let's say H1 and H2. So you choose the basis like that, then add H. So add H, this is 8 by 8 matrix. So add H is anyway diagonal, right? That was the whole point, right? We found the eigenvalues, right? The roots were defined precisely from this. H x alpha I was equal to alpha I H x alpha I. No? So what it means is that add H acting on x alpha I is equal to this quantity. So add H is diagonal completely. So if now let's write down what are the diagonal elements. So here it will be alpha 1H, here it will be alpha 2H, alpha 3H, and then minus alpha 1H, minus alpha 2H, minus alpha 3H, and finally the last one, H1, H2, they commute. So if you replace this by H1 or H2, that will of course commute with the H. So it will be right hand side will be 0, right? So those will be the 0 eigenvalues. So you see everything else, this is all diagonal, everything else is 0. That is what add H will be. So if I now take the add H times add K, so K will be the same, add K will be the same as that, except it will be alpha 1K, alpha 2K, and so on and so forth, right? So now I take the add H times add K matrix, take the matrix product and take the trace over it. So what will be add H times add K? It will be just a product. And product, since it's all diagonal, it is a simple product of diagonals. So add H times add K. this is same as alpha 1h, alpha 1k, and so on. Alpha 2h, alpha 2k, right? And the last two elements will be 0, 0. And notice that when I take so it will be minus alpha 1 of h times minus alpha 1 of k. The minus minus becomes plus. So this will be repeated, right? So here will be alpha 1h again, alpha 1k. So there is alpha 3. And now, so once I have taken this matrix, what I have to do to compute the d of hk is simply take the trace of this matrix. So this will be the trace of that. But the trace is simply, everything else is 0. Just you have to take the diagonal trace, and that gives you immediately that formula. It gives you the formula that it is simply sum over alpha ih, alpha ik, with a factor of 2, because each of them appears twice. I mean, this one is appearing twice, this one will be appearing twice, so it's a factor of 2, and sum I going from 1 to 3. That's the right. So now we can compute what is the BH1, H2, H1, H1, BH2, H2, and BH1, H2. These are the three quantities we need to know. So let's see you remember that we had a formula which was, I think, several chapters back. Yeah, this formula was given. I think it was one of the exercise 7.3. 7.3 exercise. What we had was alpha 1 of A H1 plus B H2 was equal to 2A minus B, and alpha 2 of A H1, A and B are arbitrary numbers, BH2 was equal to 2B minus A. So we had, this was the exercise 7.3, right? You remember that?
8.4. 6.3.
8.3, is it? Okay. So there's a typo here actually. By the way, there are several typos here. Not important typos, but I mean typos like this. So 8.3. 8.4, okay. Yeah. Okay. So we can then find, right? So it means, for example, so what does it mean? Alpha 1, this means alpha 1 of H1 is equal to 2, alpha 1 of H2 equal to minus 1, and alpha 2 H1 equal to minus 1, and alpha 2 of H2 is 2. So we can compute this here now. So this is the formula which we want to compute. So this is the same as 2. So we can write it as 2 alpha 1h alpha 2h plus alpha 1h plus alpha 2 k alpha 2h alpha 2k plus alpha 3h alpha 3k. But we know alpha 3 is equal to alpha 1 plus alpha 2, right? So we can also write this down explicitly. So this is this 2, so that we don't have to keep. So let me just write that down. So what is alpha 3 of H1? So we said alpha 1 of H1 is 2, etc. So alpha 3 of H1 is simply alpha 1 of H1 plus alpha 2 of H1, right? So 2 minus 1 is 1, and alpha 3 of H2 is equal to alpha 1 plus alpha 1 of H2 plus alpha 2 of H2, which is again 2 minus 1 is 1. Okay. So let's substitute that here. So okay, now let's compute each of them. So let's look at the BH1, H2. So B H1, H2 means I'm looking at H equal to H1 and K equal to H2. So this is H1, this is H1 again. So H alpha, I look at H1, H1 first. So I just substitute everything H1, H1. So this one is 2, so 4. This gives you 4. This one, it gives you 1, minus 1, but that is 1, plus 1. So plus 1. And this one gives you, again, 1 times 1, plus 1. So altogether you get 2 times 6, which is 12. So this is 12. And similarly, you can see that B of H2 is also 12. For the same reason, right? If I look at H2 here, then this will be 1, that will be 4, and this will be 1. So result is the same. And finally, B H1, H2. Let's look at that here. So now I have to substitute here H2, and H2 here. Okay, so alpha 1 of H1 times alpha 2 of H2. Alpha 1 of H1 times alpha 1 of H2 is 2 times minus 1, so it's minus 2. This is minus 2 here. And alpha 2 of H1 times alpha 2 of H2 is also minus 2. Minus 1 times minus 2, minus 1 times plus 2, so it's minus 2. Okay. And finally, alpha 3 of H1 times alpha 3 of H2, both are 1 each, so it's plus 1. Okay. So minus 2, minus 2, minus 4, minus 3 times 2, so minus 6. So these are the information we need. I hope I have not made any mistake here. It's easy to make some silly mistakes. You have checked, all of you? Right? It's okay. Okay. So now we proceed further. So essentially, so what the Karnath-Killing form has given is a nice, very good metric on the space of no. So it has given a nice metric on the space. Because you see, to begin with, you had Lie algebra, which was a vector space, but we didn't have any notion of distance. A metric gives you a notion of distance, no? Or dot products between two different vectors. So this is giving you a notion of metric. So what is happening? I mean, you see, before we were talking about the vector space V, or the Lie algebra V, or more precisely, let's say Karnath subalgebra, which is a subspace of the full Lie algebra, right? Now we have defined the metric already on the Lie algebra itself.
Isn't the metric supposed to be like a matrix, like eta?
Yeah, that is a matter of choice of basis. You see, I mean, what this is computing is give me any B of some element x and some element y. B of xy, where x and y are arbitrary elements of the Lie algebra. Then it is giving you an inner product between the two. Right? Now, that is done in the section 11.1 to choose a basis and write it in like that. So that is what the metric does. I mean, say when you're given a metric, so this is some particular vector in the space x and y. What you want is some kind of a formula, some kind of a rule which tells you what is the x dot y. Right? If you use a basis, then you will write it as xi, yj, eta ij, or delta ij, or gij, metric. So yeah, you can of course expand it in terms of choose any basis. Ti, let's say, is a basis. Is a basis for V. Then I can expand everything. X is equal to some xi ti, and y equal to some yj, tj, summed over I. So for example, for SU3, this I will go from 1 to 8 because it's 8 dimensional. So you have to choose the 8 basis vectors. And then if you substitute that here, then so if I want to compute this bxy, that's the same as xi, yj, b, ti, tj. Right? Because these are numbers, and you know that this is bilinear in x and y. No? So you can take that out. The coefficient, these coefficients can be taken out. And you have b, ti, tj. Call this, let's see, what is the name given here? Any particular name? I think it's just called bij here in these notes. Right? Just give a name. It will be something, whatever, some number here. Call this bij. Then bij is your metric. I mean, in the standard.
So we can suppose that the first two numbers are like the diagonal component.
Yeah, that's right, that's right. But this is, of course, restricted to the Cartan. No? To two-dimensional subspace.
So the Cartan is not like a flat vector. It's kind of curved, right? In a way.
Well, not. I mean, this is just telling you what. I mean, you can think of a flat space where I have just two vectors here in the flat space. I have two vectors, h1 and h2, such that I mean, you know, it should be the minus sign. So it's some angle here, and h1 is its length is 12, or length square is 12, and the dot product between these two is minus 6. That you can visualize it in the flat space. That's not a problem. Yeah. Okay. So I mean, if you want to think that this was the purpose of the first section, where kind of one is reformulating it in the standard language. In the standard when you say metric, as you say, metric you think of a tensor is a tensor, symmetric tensor. No? But symmetric tensor, you see that at this level. Once you choose a basis, then you get this bij's.
Professor, and then the orthomorphism that we saw is kind of a
Sorry, repeat it.
The orthomorphism that we saw is kind of a change of basis matrix. Can it be seen as a change of basis?
Yeah, you can think like that. Yeah. So automorphism will take Ti and Tj to some Ti prime and Tj prime. So,
And Professor, BH2, suppose BH2 is 2, it gives us dot product of H2 with addition of H2 with addition of H2. It means that the length of H2 is 12.
length square is 12. Yeah.
Length
square is 12. And so yeah, this is the So this will be the like length square. Huh? Length square. Also this is length square, and that is the dot product. Dot product would mean length of this times length of that times the cosine of the angle. No? I mean, this particular thing is not so important, right? Because okay, this was just a choice of basis. I mean, we could have chosen something else. You know? H1, okay, in that, if I choose some other basis, not H1, H2, but some other basis, it has to be, H1 and H2 are what? It's just some special traceless diagonal matrices, right? But I could have chosen something else, for example, lambda 3 and lambda 8, no? Lambda 3 and lambda 8, it would be, they're orthogonal, no? Lambda 3, if you take B of lambda 3, lambda 8, it is 0. So it's a matter of choice of basis. It doesn't have. But what we will see now, that there's actually something very geometric about the roots when we talk about the roots. Okay. We will see that now. Okay. So what did we do here? I mean, so we had this. There was a subspace which we called the Cartan subspace, which was, I think we were denoting as script H. No, script H was the Cartan subspace. So in SU2 case, it was two-dimensional. This was two-dimensional in SU2 case. SU3 case, sorry. And for one-dimensional in SU2 case. That was the H. And now, before introducing this metric, I mean, this we were discussing already before we introduced the metric, right? What we did, I mean, we said, okay, let's look at the linear maps from H to numbers, okay? And that is how we define the dual vector space. we said there's a dual vector space, H star. This is a dual. This is a dual to H. What it means is that every element of this, so the roots were living here, right? The roots were living here. All this alpha 1, alpha 2, etc. These guys are living in the H star, the roots, in the dual vector space. That is why we said alpha of H is a number, So alpha is a dual vector, H is a vector. So I say this I call vector space, original vector space. This is a dual vector space, so it's a dual vector and a vector, and that gives you a number. So in some sense you can think of it like this. So suppose I had chosen some basis here. So let's say HI, H1, H2 for example. So I can choose a basis here. So I put always the index, lower index for a vector. Now this I will denote always with the upper index, or vice versa, it doesn't matter, that's up to your choice, that's your choice. But choose some convention, say I will always put in lower indices to the vector and the upper indices to the dual vector. Okay? Then by this I would just mean summed over I. So these are some numbers, they are the various components of this dual vector, so each of them is a number. And these are various components of the original vector, H, in the original vector space. Again, these are numbers. So when I take this thing, this is going to be some number. No? So you can think of this think of a dual vector and the vector as something which comes with a covariant and contravariant index. Lower and upper index.
We're talking about the components of the P.
Components of the, yeah. Exactly. So now, but there is no natural isomorphism. It is true that both are same dimensional vector spaces. Any two vector spaces which are of same dimension, they are isomorphic to each other. Okay? But there is no natural isomorphism. As it is, here you have this vector space and dual vector space, there is no natural isomorphism. No? From H star. So I want to, isomorphism meaning that every element of H star, I map to H or vice versa. So it's a one-to-one map. Okay. That is what is isomorphism. A one-to-one map which preserves a vector space structure. Because these are vector spaces, so you want to preserve the vector space structure. So this will be one-to-one map. There are infinite number of ways you can do these maps. That's not no particular problem. But there is nothing natural about this map. The moment you have metric, and the Cartan killing form is a metric. The moment you have a metric, then there is a natural isomorphism between the dual vector space and the vector space. And the way you do it is you can use the metric to lower or to bring the upper index to lower index or lower index to upper index. No? Because if I have a metric, then if I have a metric, let's call it Gij, this is the metric. Okay. This Cartan killing form, whatever it is, it gives you. So I have chosen a basis. I compute the B of Ti Tj. That I call, okay, I think here we're calling Bij, let's say. So Bij, I have this the metric. Now, if it is invertible, this is the important point. If it is invertible, right? This is a matrix, right? I goes from 1 to the dimension of H. J also goes from 1 to the dimension of H. So it's a square matrix. No? Now, if the square matrix is invertible, okay, then you can talk, then the B inverse exists, right? So if the determinant of that is, if the determinant is, what does it mean invertible? It means the determinant of this thing is not 0. Determinant of B is not equal to 0. Determinant of B restricted to the Cartan. So this is just for the Cartan, I'm talking about Cartan. So B is defined in the full Lie algebra, but restricted to the Cartan. So it will be, for example, for SU3, the B was defined for all the 8-dimensional space, right? But now we restrict ourselves to the Cartan part. So it's in 2 dimensions. So B restricted to the Cartan. So it's a 2x2 matrix for SU3. So if that matrix is invertible, okay, that means if determinant is not 0, then of course I can define an inverse. So inverse, I define it with a index up, Bij up. This again a 2x2 matrix. for SU3. So I denote it like that. Now I can use this to go from H star to H or vice versa. Right? For example, if I give you an element in H star, if I give you some element alpha I, then I can define this Bij here and define something which is alpha j down with a lower index. So you are giving this is an isomorphism, okay? It's a map from the dual vector space to the original vector space, but it's a natural isomorphism. It's something which is singled out by the metric. So it is this thing we can use. We can use this to map these roots, alphas, to some particular elements in the Cartan subalgebra. Okay? Which was not, in the beginning you had no such map. But this Cartan killing form, this metric, allows you to have such a map. Okay? So our idea now will be to map this alpha 1 and alpha 2 to some specific elements. No? Alpha 1 will be mapped to some particular element, alpha 2 will be mapped to some particular element in H, in the Cartan subalgebra. That's one. The second thing that metric can do is that, just like we said, so we had, I'm sorry, actually I made a mistake here. Okay, I was using, sorry, maybe I should have put the upper index here, HI, and lower index here. So choose the original, because I choose the Bij to be the Cartan. Okay. So I put the upper index here. This is the Cartan, and that is the dual. So this is a vector space, H, and this is in the dual vector space. Okay. So just like Bij was giving you a metric on the vector space, this B inverse Ij will give you a metric on the dual vector space. Okay. So you can define then a metric structure in the root space, in H star. You can talk about the inner product of between two different roots. Okay. See, here we have talked about the inner products between two Cartan generators. So in other words, in the H. Okay. Now using this step, we can define an inner product in the root space itself. Okay. In the dual vector space. Directly we can talk about the dot product between alpha and beta. Say alpha and beta are two roots. We can talk about the dot product between them. So this is the main thing of the remaining part, 11.2, section 11.2. Okay, so let's define it like this. So, okay, is the idea clear? I mean, I'm sorry.
In this case, Professor, alpha I, is this like Bij? Like it's mapping one component from here and the other from here, right?
I mean, maybe I should have actually what I did. I mean, so this.
It's like alpha I, HI, Bij. Alpha I contravariant, HI contravariant, Bij, and this is that, right?
Yeah. So I mean, we are saying that we are expanding the basis. So for the H, I chose a basis which I call Ti, Tj, etc. No. This basis. I mean, this is in the Cartan, so I don't know how shall I call it. H1 and H2, let's say. Yes? H1 and H2. I chose this basis. Then an arbitrary element of H, arbitrary element H will be some number xi, hi, right? Some door I. This is an arbitrary element. So really, I should be calling this xi, let's say. So this is what is H in a particular basis. In a particular basis, I denote H by giving all these numbers xi. Once I specify this xi, then since I fix the basis, then I know precisely which H I'm talking about. So the information is the same here. Now, in the same way, in the dual vector space, I can choose some other basis. So in H star, I can choose some basis, some other basis. Let's say here I chose H1 and H2. So let me choose the basis H1 and H2. Okay. In this here, with I can define it that H1 times Hi with Hj is delta Ij. Okay. So these are special functions. You remember this elements of H star. Some elements of H star are linear functions from the vector space to numbers, right? So what does H1 do? H1 is an element of H star. H1 is a particular element which takes H1, small h1 to 1 and small h2 to 0. Okay. On the other hand, H2 is a special, another element of another function, the linear function in H star, which has a property that H2 acting on H1 is 0 and H2 acting on H2 is 1. Okay. So this is a choice of basis. I've chosen a particular basis. It doesn't have to be this. I could have chosen any other basis, but it's a convenient basis. Okay. So once I've chosen the basis, any element of H star, so if alpha belongs to H star, then I can always write alpha as alpha I, Hi. No? Where alpha I are numbers. So according to this definition now, how does alpha act on an arbitrary vector? It is by this, alpha I xi, right? I mean, H is an expanding H, any element H, as some number xi, hi, where hi are the basis vectors. Then if you take alpha to be this object, then you see the alpha H is nothing else but that. So you see what I'm saying? I mean, so in other words, hi is defined by this equation. Okay? So this defines, and then you can see immediately if you apply this this guy on that. These are numbers, so I take it out. Then hi with hj is delta ij, so you just get that in a product. I'm not in a product. That's the way the alpha acts on H. Okay. So this is the steps we'll be doing now. I don't want to erase this. This I should keep it. Okay. So what is so far I was working with the basis, but all of these things can be just said without any basis, without choice of any basis, and I'll be basically following that. I mean that is how it is given in the notes. But you can translate every single statement here by going to a particular basis in this language. Now, so the statement is the following. So we can define, so I'll be assuming. So first assumption here, is that B restricted to the Cartan subalgebra is invertible. Right? I mean, this is certainly the case for SU3, right? Because, I mean, if in this basis, H1, H2, it looks more complicated. But if I had gone to lambda 3, lambda 8 basis, right? This B is simply 1, 1. So 1, 1 or some particular number. 2 times delta AB or something like that. So it's just a diagonal identity, proportional to identity. So it's invertible, of course. Right? We will show in when we go to the next chapter that in the class of algebras we are talking about, this is always true. This statement is always true. So it's quite general. This statement is quite general. If that happens, then I can define, for a given alpha, I can define a particular element, I call it H alpha, okay, which is so this is an H star, and this is an H. So this is the dual vector space, and that is in the vector space. So I can define a map, okay, and that is defined like this. That alpha of k is equal to B of H alpha k, for all k belonging to H. This definition is the same as what I was talking about before in the component form, when I chose the basis. This definition is the same. Because you can again expand k in terms of the basis for the Cartan subalgebra, and then this will again this H alpha can also be expanded in some Cartan basis in the basis. Then this I can rewrite it as H alpha I K I B I J. No, you can write it. So it's the same formula, but I don't put the indices and so on. No indices, but it's exactly the same content. Okay, so what is the statement here? So alpha, this side is a linear map from the vector space to numbers. Okay. Now I'm saying this now for every k in H. So for every k in H, we want to look at this equation and see if we can find some H alpha. If I can find some H alpha, then that is what alpha is mapped to. This is both in the vector space. Both of these guys belong to H. Okay. This is in the Cartan subalgebra. It's not a root, but this index is just denoting that alpha maps to this particular element of the Cartan subalgebra. Of course, if I change this root, of course this will be changed also. So this, just remember, that this is a map of which root. Huh? So that is why this index is alpha. Okay. Now this can be, you can do the same thing that we did before, expand both sides on the basis, on some basis, and then you can see that if Bij were invertible, if the B is invertible, there is a unique solution for this equation. Okay. So if B is invertible, B restricted to, if this is true, if this statement is true, if this holds, then there is a unique H alpha, the solution of this, solution of this equation, which solves the above equation. It solves this equation. There's a unique H alpha. So this is a very important concept here. Now, of course, this need not be the case. You could have put any number here. Okay, it's not. That's up to you to define. You can put some number here, which is denoted here in the definition 11.3. You see, there is some number here which is denoted by CG. This is not important at all. This has no consequence at all. You just choose this number for convenience. For example, you want to get some nice integers, so then you can choose some normalization, overall normalization. This doesn't depend on which element you're talking about. This is a universal number, okay, for a given Lie algebra. You choose it as some universal number. Okay. Typically, it turns out to be convenient to choose for SUN. One chooses CG equal to, I think, 1 over 2n. 1 over 2n, I think. Yeah, 1 over 2n. For SU. But it's completely irrelevant, this number. In none of the calculations, this number plays any important role. Okay? It is just so that we get some nice numbers. We don't get, like for example, lambda 8. I hated lambda 8 because of the root 3. So you don't want to come up with some horrible numbers. So it's just for that reason. There's nothing more than that. Okay. So this is the first step. And the second thing is, as I mentioned to you, that if the B is invertible, then I can also talk about a metric in the dual vector space directly. Right? This metric is in the original vector space, in the H space. Yeah? But now if the B is invertible, then I can define also a metric in the directly on the in the H star, okay, which is basically the inverse of the B. No? So that you define in the next line, in the next equation, is defined as the following. So this allows us to define a metric in the root space directly, which is denoted here, not exactly, just like that, alpha beta. So this is both are in the H star. So both alpha and beta are in H star. As this is nothing else but again the same CG, B of H alpha, H beta. So this is exactly the idea which I was mentioning before, because you see this gives us a canonical map from the root to the original vector space, right? From the dual vector space, alpha is in the dual vector space. So you see alpha and beta are in H star. And then you have H alpha and H beta are in the original vector space, H. So this has been mapped there, this has been mapped there through this equation. This equation is giving a canonical map, alpha to H alpha. And now I just define the inner product between these two as the inner product between these two up to some number. That's what it is. This is the inner product between H alpha and H beta. This was the inner product defined in the vector space, H. But using that, I define an inner product in H star. So this is that idea. Okay, so let's just take some examples. Okay, SU2 example is too trivial. I mean, you can take a look at that, 11.22. That is for the SU2. But now let's look at SU3. That's a bit more interesting. So let's. So we want to. We have these roots alpha 1. The H1 alpha 1 and alpha 2. Of course, alpha 3 is alpha 1 plus alpha 2. So if I know where alpha 1 and alpha 2 are mapped, then I also know where alpha 3 is mapped, right? So because all maps are all linear. These maps are linear. So we can ask the question, what is, so we are asking the question, I think I can erase this part. No, I can erase this part. So maybe I just write this equation here. Where this H alpha, so where H alpha is defined through this equation, alpha k equal to Cg B H alpha k for all k in H. So that's how this is defined. That's how the definition of H alpha. And once I have the definition for H alpha and H beta, then I define the inner product here. Now I can erase this part here. So let's just compute. So first of all, let's look at what is H alpha 1 and H alpha 2, where alpha 1 and alpha 2 for SU3, the standard alpha 1 and alpha 2 we were using. No? The alpha 1, the roots alpha 1 and alpha 2. So what we have is alpha 1. Now this formula was, that formula, right? So alpha 1 of H1 is 2, right? So we have this equation. So let's find out what is, I first look at this equation, alpha 1. So I look at alpha 1. So question is now, for alpha 1, what is H alpha 1, the map. So this one is mapped to which element of the Cartman subalgebra? So we want to find that. Well, our defining equation is this, right? Sorry, that one over there. So what we want is alpha 1 of k, arbitrary k, should be equal to Cg BH alpha 1, comma k. This should be true for all k. Right? But you know, we have a basis for any k I can write it as some number, let's say k1 h1 plus k2 h2. Right? Because h1 and h2 are a basis for the Cartan subalgebra. No? So it is enough, by linearity, you see, it is enough to just make sure that we have this equation splits into two equations. Alpha 1 of h1 is equal to cg b h alpha 1 h1 and alpha 1 of h2 equal to cg b h alpha 1 and h2. Right? If I have satisfied these two equations, then of course it's obvious that it's true for everything, right? Because I just have to when I substitute that here, you use the linearity, you can take out k1 and k2, no? The two terms, and if they are satisfied, it's automatically satisfied, right? That's the nice thing about it. I mean, for all k, you would say that's horrible because there are infinite number of k's, no? So am I going to look at each infinite number of equations? No, not possible, right? The point is that this is linear. So therefore, it is enough to check it for the basis. Choose some basis for the vector space where the k lives. And if this is true for that basis, then it is true for the whole thing. So it's not infinite number of conditions here. There's a finite number of conditions. There are as many conditions as the basis. So in this case, there are two conditions. Okay? So now we already know, so alpha 1 of h1 is 2. Alpha 1 of h1 is 2. And alpha 1 of h2 is minus 1. So you want to look at these two equations. Okay. Now, h alpha 1, whatever it is an element of the Cartan subalgebra. Okay. So I can always expand h alpha 1 as something, some number, let's say x h1 plus y h2. Right? This is the most general expression for h alpha 1, where x and y are some numbers which we do not know yet. We hope that we can determine x and y from these equations. So let's substitute that here. So here, if I substitute that, so let's see what is b h alpha 1, h1. That's the same as b of x b h1 plus y b h2 h1. Right? Again, I use the linearity property of the thing. I substitute that here and use the linearity condition. Okay, you get that. Now, we have already calculated that. So BH1H1, so this is 12x plus BH2H1 is minus 6. So minus 6y. Okay. So this side, and let me just substitute CG. For the CG, we said CG is 1 over 2n, and we are talking about SU3, so it's 1 over 6. That is the reason for choice, 1 over 6. You see the factors of 6 cancel. So it just makes the life easier. No, there's no other reason. So this becomes, so right-hand side becomes 2x minus y. That equation. Okay. What about here now? So we do the same thing. Now with the H2. So here it's H2, H2. Right? So BH alpha 1, H2 will be the same expression, but the second argument is replaced by H2. So it becomes x, B of H1, H2, which is minus 6. So minus 6x. And H2, so now this is replaced by H2, so it's H2, H2, which is 12. So plus 12y. Okay. So once again, if I substitute, put a 1 over 6 here, then this 6 factor cancels out, then we get minus x plus 2y. So we have to there are two equations for two unknowns, x and y. Okay? And we can determine them x and y. I mean, generically, but okay. So we can substitute, so this, for example, if I solve this equation, for example, if I solve for this So from the first equation, I get y is equal to 2x minus 2. Now substitute that here. So this becomes, so here it becomes minus 1. Second equation becomes minus 1 minus x equal to minus x plus 2y. So plus 4x minus 4. Right? So this means, so I can take this on the other side. Okay. This means 3x equal to 3. Right? This 4 I take it out, 4 minus 1 is 3, and 4x minus x is 3x. So therefore x is 1. X is 1. And if x is 1, y is 0. Okay. So we conclude then that that h alpha 1, where did I write h alpha 1? Yeah, h alpha 1 therefore is simply h1. Because x is 1 and y is 0. So so this is the solution. So that means alpha 1 is mapped to h alpha 1, but h alpha 1 is simply h1. So okay. You repeat the same thing for h2, alpha 2. If you do the same thing for alpha 2, you will find the calculations are very similar. I mean, now it just gets exchanged, you see. If I put alpha 2 of h1 is minus 1. So this will become minus 1 and that will become plus 2 if I change to alpha 2 here. And again, here again some things will change. No, here it's the same, right? Right hand side is the same because I just call this h alpha, h alpha 2, where h alpha 2 is, okay, so I'm saying, so first of all we already concluded, let me write down here, that h alpha 1 is h1. This is the answer. Now let's do this for alpha 2. So I just put here alpha 2, okay, and then, but of course here alpha 2 of h1 is minus 1, so this becomes minus 1, that becomes plus 2. From that, alpha 2 of h2 is 2. And here's h alpha 2. And we have again these equations, but now let me write h alpha 2 is xh1 plus yh2. Then nothing changes here. This is the same, 2x minus y. I mean, I'm just calling this as xh1 plus yh2. So this equation is the same. So now you see that the role of x and y has changed. Right? Before 2 was there and minus 1 was there. Okay. Now just x and y have changed. So for example here, this tells me that x is equal to 2y minus 2. So this equation tells me x equal to 2y minus 2. Substitute that there. So this becomes 4y minus 4 minus y. So 3y minus 4. Take the 4 there. So 3y equal to 3. So y is equal to 1 now. And if y is equal to 1, x equal to 0 also. So we find that h alpha 2 is h2. So it's a very simple thing. H alpha 1 and h alpha 2 are very simple. I mean, simple meaning that it was directly given in terms of h1 and h2. Now, you notice one important thing here. Now, remember the x alpha 1, this was for the alpha 1. Which was the SU2 subalgebra generated for the alpha 1? We remember for every non-zero root, there was an SU2 subalgebra. Right? The SU2 subalgebra was basically x alpha 1, x minus alpha 1, and h1. That was what was forming one SU2 subalgebra. Okay? And we notice that the h alpha 1 is in fact equal to h1. So what we are saying, alpha 1 is mapped to, by this map, this map, it is mapping to a particular element in the Cartan subalgebra, which happens to be the same one which is inside the SU2. Okay? And the same thing happens for x alpha 2. If you look at the SU2 generated by that, it was x minus alpha 2 and h2. This formed an SU2 subalgebra. That formed an SU2 subalgebra. Right? So you notice this coincidence. I mean, at this stage it's a coincidence, but we'll see it's a completely general phenomenon. At this stage it's a coincidence that this rule that we have given here, the map, from the dual vector space to the vector space, it is actually mapping precisely to the Cartan element which makes it an SU2 subalgebra. Okay? Not some arbitrary Cartan. It's that Cartan which makes it SU2 subalgebra. Okay. That's an important point, which we will come across. We'll see complete generality later. Okay. So yeah, this was the edge of. Okay, given this, now we can use the second equation to define an inner product between the roots, right? So before, is there any question? It's important to understand.
So it's like map the point to itself. It's mapped H. I mean, alpha 1 has mapped H1 to.
No. This is the map of alpha 1. This map is alpha 1. Alpha 1 is being mapped to H alpha 1, right? And this is alpha 2 is being mapped to that. Here is H star. These are elements in H star. These are elements in H. So we have given a map via that equation, which is mapping a root to a particular Cartan element. But what I'm saying is that that map is such that this Cartan element is H1. And I mean, alpha 1 defines to you this. This is the corresponding root vector, right? This was the root, and that was the corresponding root vector. And the x minus alpha 1 was the the root vector corresponding to minus alpha 1. And we said that these three are forming one SU2 subalgebra. So what I'm saying here is that the map from alpha 1 to the Cartan subalgebra is not random. It is actually precisely going to that element. You know, not some H1 plus H2 or something, some combination of H1 and H2. It's going precisely to H1. No? I mean, if I had added x alpha 1, x minus alpha 1, and some combination of H1 and H2. I don't know, let's say x H1 and something, I don't know, small x H1 plus small y H2. This will not form an SU2 subalgebra. It's exactly that, H1. Because, I mean, you can see that if you look at the commutation, I mean, if you, this I shouldn't erase. The fact that SU2 subalgebra comes from just this here, right? I mean, if I look at x alpha 1 commutator, x minus alpha 1, what did we get? We got H1, maybe some number, but no combination with H2. No? So this is not, I mean, if I add an H2, it's not going to be subalgebra. No? Subalgebra means there should be, I mean, whatever it appears there should be that, no? It's the subalgebra. So it's really it's this combination. These three guys generate one SU2 subalgebra. This guy generates another SU2 subalgebra. So it's interesting, yeah. Because I mean, naively you would have thought, okay, I mean, this rule would just give me some combination of H1 and H2, no? And this is also going to be, but no, it picks up exactly that guy. It doesn't. So that we will see in complete generality later. Huh? This may look like just an accident for SU3, but it's not an accident. It's general. Okay. Now let us go to the here. So far we only analyzed this equation, right? Now let's look at this equation. So it is giving a metric directly in the root space. No? So since we already know the H alpha 1 and H alpha 2, etc., then we can immediately find out what are the. By the way, you can also check H alpha 3. I mean, it's not H alpha 3 is not surprising, right? Because H alpha 3 is going to be simply H1 plus H2. Why? Because alpha 3 was alpha 1 plus alpha 2. And that's why linearity of this equation, right? H alpha 3 is going to be simply H alpha 1 plus H alpha 2. Not this equation, sorry, that equation. I mean, if you plug here alpha 3, then it will be alpha 1 plus alpha 2. alpha 1k plus alpha 2k. And here you'll have H alpha 3, but then for alpha 1k, so if you substitute H alpha 3 equal to H alpha 1 plus H alpha 2, is automatically satisfied, right? I'm just saying that, suppose you take alpha 3 here. So it will be alpha 3 is the same as alpha 1k plus alpha 2k. Okay. But for alpha 1k, I already know that this is the same as Cg B of H alpha 1k. And this guy is also Cg is a common factor, B H alpha 2 comma k. Now use the linearity property of the Cartan-Killing form. That's the same as B of H alpha 1 plus H alpha 2 comma k. Correct? So therefore, alpha 3 would be mapped to alpha 3, H alpha 3 would be mapped to H alpha 3, which is H1 plus H2. And again, if you look at the corresponding SU2 subalgebra, it is X alpha 3, X minus alpha 3, and H1 plus H2. This was the corresponding SU2 subalgebra. So every time it is that element which appears in the SU2 subalgebra, that is what this is mapped to. Okay, so now we go to the next, we now try to directly write down the metric structure of the alpha on the alpha space, and that we can do using the next equation. Then I can erase all this. Can I erase all that? Okay, so let's look at now that equation. So we have alpha beta equal to. So let's look at what is alpha 1, alpha 1. Let's compute that. We can compute all of them. So let's take alpha 1. You get from this equation you get a 1 over 2n, 1 over 6. Okay, and let's say b of H alpha 1, which is the same as b of H1. Right? H alpha 1 with H1, which is 2, because this is 12 in that table there. Similarly, alpha 2 is again the same thing, 1/6 dH2H2, which is 2 again. And finally, let's also look at alpha 3. That's again 1/6. Now, we said alpha 3 is mapped to H alpha 3 was H1 plus H2, right? So this is going to be B of H1 plus H2, comma H1 plus H2, right? Now use a linearity. So this is the same as, so this will be 1/6 B of H1 plus B of H2 plus there are cross terms H1 H2 and H2 H1, but B is symmetric, no? So this becomes 2, factor of 2 B H1 H2. Okay. So what do we get here? So 12 plus 12 plus 2 times minus 6, so that is a minus 12. So minus 12, 12 cancels, so you again get 12. So this is again 2. Okay, that was the diagonal ones, alpha 1 with alpha 1. But now we look at the cross terms. So what about alpha 1 with alpha 2? Is this? So alpha 1 with alpha 2 is 1/6 B H1 H2. Which is H1 H2 is minus 6, so it's minus 1. What about alpha 1 alpha 3? Well, that's the same as 1 over 6 B of H1 comma H1 plus H2, because alpha 3 is mapped to that. So now you look at that H1 is 12. and H1, H2 is minus 6, right? So 12 minus 6 is plus 6. Something is wrong. Oh, so this is plus 1. This is plus 1. Huh? So this is, BH1, H1 is 12. BH1, H2 is minus 6. So 12 minus 6 is 6. And finally, B alpha 2, alpha 3 is again the same thing, 1/6 B H2, H3, H1 plus H2. So H2, H2 is 12, H2, H1 is minus 6, so it's again plus 1. Right? But this is exactly the hexagon we drew. This is exactly the hexagon we drew. Except that now this precise number is because of all these. Okay, no, not okay. This number is overall number is not important. There is a relative ratios are what is important, because you could have scaled the length. That's not the problem. But the point is that so here is, since we are saying that alpha 1, so length square of alpha 1 is 2. So alpha 1 is like root 2. Length of is root 2. Whereas what we were drawing before, I think it was length square was 4 probably, right? When we were drawing the previously this diagram, no? The hexagon we drew. But here it is just length root 2. So if I draw in a 2 plane, alpha 1 is length root 2. Say this is alpha 1 in 2-dimensional plane. And then alpha 1 with alpha 2 is, this will be the length of alpha 1 times length. So the lengths are same. You see, lengths are all the same. Alpha 1, alpha 2, alpha 3 all have the same length. Root 2, root 2, root 2. Now alpha 1 dot alpha 2 should be length of alpha 1 times length of alpha 2 times cosine, the angle between the two. So root 2 times root 2 times, so 2 times cosine is equal to minus half. So cosine is minus half, right? 2 times cosine is minus 1, so cosine is minus half. Therefore it is 120 degrees, right? So say I draw alpha 2 somewhere here, but the same length, 120 degrees. So this angle is 120. Okay, this is alpha 2. What about alpha 3? So alpha 3 again has the same length, but now it is the cosine of the angle between alpha 1 and alpha 3 is plus half. Root 2, so 2 cosine theta is 1, so it's plus half. And here is also plus half. So both are 60 degrees, right? So alpha 3 is making an angle 60 degrees with alpha 2 and alpha 3 both. So alpha 3 is in this direction. Not in that direction, because that would be 120, 120. No? So this is alpha 3 and the same length. This is exactly what we found. Okay, because then there is a minus alpha 1, minus alpha 2, minus alpha 3, so it produces exact hexagon. It's all completely independent. That diagram we drew with when we kind of plotted lambda 3 and lambda 8 eigenvalues. No? Here we are not choosing anything. No? There's nothing at all. No such basis. It's just a purely geometric thing is appearing there. Okay, so this is the. Okay, now. So what is the time now? Okay, let me. Okay, if there is any question here, let's first pause here. Any question? Then let's move on to the chapter 12, but just the beginning because there was not too much time. Yeah, just the beginning. Okay, any questions on this? Any questions from here? Questions, comments? Okay, so then shall I move forward to the next chapter?
Just one question.
Yeah.
If H1 and H2 are not orthogonal, right?
H1 and H2, yeah, from that angle, that thing is the H1 H2 was minus 6. Yeah.
The hexagon are supposed to be not regular, right? If we are H1 H2 are at our thesis, that the hexagon should be like a little bit deformed.
No, it's, I mean, this is perfect hexagon. I mean, that's what I'm saying. I mean, this is quite independent of, this diagram is not obtained by plotting the eigenvalues, no? This diagram is a bit more complicated. It's obtained by going through these two maps. But this is pretty universal maps. I mean, this is just starting from the Cartan-Killing form, which tells you what is a metric in the original space, in the Cartan subalgebra. So already this is kind of telling you what it's, if I divide everything by 6. So this again telling you that with respect, as far as Cartan-Killing is concerned, H1 and H2 are 120 degrees. If I drew a similar diagram, this was a diagram in the root space, a dual vector space, right? That would be the diagram in the original Cartan subalgebra. Yeah. So one is plotting H1 and H2 like 120 degrees, no?
So Professor, here we just first specify one vector alpha 1,
Yeah.
and then we see it's the angle between alpha 1 and alpha 2, and we draw alpha 2.
Okay, so now let me go to the, I think, can you erase all this? Let me go to the chapter 2, chapter 12. Now these are again some very important concepts. But I'm not going to prove many of the statements because that will take me very far from the, maybe I'll just try to kind of motivate why that makes sense, but not a rigorous proof. Okay, let's leave it. So chapter 12, so we start with it. Now here there are some definitions. Okay, so one definition is, there are some algebras which are called simple algebras, simply algebras. Okay. So the first definition here is a definition. Okay. The definition is that so a simple algebra is defined as an algebra which has no proper ideal invariant subalgebra. Remember we defined invariant subalgebra. So this has, by definition, it has no proper invariant subalgebra. Proper meaning that it should be really a subalgebra, not, I mean, of course you can take the algebra itself. That's a trivially invariant algebra, no? So something which is smaller than the original algebra. So proper invariant subalgebra. I think one has to exclude from here because, I mean, this will allow you to have except for U1. I mean, U1 would satisfy this condition, right? U1 is just one-dimensional algebra. Well, no, U1 doesn't satisfy. No, sorry, it's okay. No proper invariant subalgebra. Invariant subalgebra. So no proper invariant subalgebra. Yeah, I mean, subalgebra which is not null, not a null subalgebra, meaning zero dimensional. No? I mean, this could be if you take it to be empty. Of course, so apart from this obvious things, I mean, so something which is a proper but non-zero, non-null subalgebra. That is what's called a simple algebra. So examples were, I mean, for example, SU2. That we studied SU2, SU3, both of them are simple algebras. SU2 had no invariant subalgebra, no non-trivial invariant subalgebra, proper non-trivial invariant. SU3 also didn't have, SU3 had a lot of SU2 subalgebras, but they were not invariant, right? Because, for example, if you look at x alpha 1, x minus alpha 1, H1, this formed in SU2 subalgebra. right, of SU3. But this is not, I mean, for invariant, you should also ensure that the commutation relation between this and anything inside there is back in there. No? So that's not true, because if I take X alpha 2 and take the commutator of X alpha 2 with X alpha 1, yeah, then it gives you, it's not a 0, it gives you X alpha 3, right? Which is not contained there. So this is not an invariant subalgebra. So the question is about invariant subalgebra. Of course, there are many different subalgebras, right? But they should not be invariant. That's the main thing. So both of these are examples. U1 is not. U1 is not invariant. I mean, one has to. I think one has to remove it from here. One should remove U1 from here. I think this definition itself does not remove U1, except for U1. So forget that. Everything else which satisfies this condition is called simple. Now the second, which is second thing is what is called a semi-simple. So semi-simple, not simple but semi-simple. The algebras. So the definition is, okay, this is not, you know, if you look at any standard textbook, particularly the ones which are more mathematically oriented, this is not the way they define. The way I'm going to define, this is not the way they define semi-simple. I'll tell you how they define. But here we just take the definition like this, that if the Cartan-Killing form is non-degenerate. So that's the definition, which of course means non-degenerate means the inverse must exist. In other words, determinant of B is not 0. B is the Cartan-Killing form. So that's the definition of semi-simple. Usually in the mathematical literature, actually semi-simple algebra is defined in a different way, and defined in a different way, and then this statement is proven as a theorem. Okay, but we are just, proven as a theorem in the sense that the theorem that proves is that the statement that I'm going to make here is completely equivalent to the statement. So this implies that, that implies that. Okay? We are just choosing this because this is, I think, since we have talked about Cartan-Killing, this is more easy to relate to. No? So the other definition, so the theorem, so for us, this is a definition, so this will be a theorem. No? So Lie algebra is semi-simple if and only if, IFF, this notation, if and only if it has no abelian invariant subalgebras or ideals in the same way. Okay. It can have invariant subalgebras, but they should not be abelian. The important point is, so it can have non-abelian invariant subalgebra. There's no problem with that. Huh? The thing is that it should not have abelian subalgebra. Okay, so this, it's a bit, it looks a bit completely like different statements, how this can be related to that. So I will just give you some kind of an idea why. It won't be a proof, but it will give you some idea why this happens. Huh? So I mean, suppose, okay, what I will prove here is this, there is an if and only if statement, right? So what I will prove is that if, what I will try to argue, I mean, maybe not a proof, but some hint, that if it has an invariant subalgebra, then the determinant of B will be equal to 0. Okay. So if it has an abelian, if it has an abelian invariant subalgebra, then let B equal to 0. So it will prove only in one direction, because this is if and only if, no? This will only prove in one direction. Other direction can also be proven, but it requires some concepts which I have not introduced at all. Things like solvable algebras and so on, so we don't want to go into that. So let's look at this direction. So let's suppose, suppose we assume that it has an abelian invariant subalgebra. So I have some big algebra, let's say V, and inside there, there is a subalgebra which is contained inside. So what give some name to it? W, let's say. W is contained inside V. Okay, it's an invariant subalgebra, and it's an invariant subalgebra. So I'm calling this as a invariant subalgebra, and V is my original algebra. So let's call all the give a name some name to it. So all the elements of W I will denote by Y. So these are all elements of W, Y. So what I do is I split. So I choose, so let's say I can choose, let me choose a basis for W. So I call them Y1, Y2, whatever the dimension of that is. So if dimension of W, so Y of dim W. So this will be a basis for W. Dim W being dimension of W. So I don't know, let me sort of write it. Suppose this is n dimensional and this is m dimensional. So this will be up to m. This is not very visible, right? So I choose a basis in the following way. I choose the basis y1 up to ym. So these guys are these are bases for W. Okay? But then V, of course, is bigger than that, right? So certainly these are contained there in the V, but there will be more things, more basis vectors, right? So let me call all the remaining ones. So y, m, x, let's call it x, m plus 1, up to whatever xn. So these are not contained in V, but of course contained in W. Not contained in W, but of course in V, but belong to V. So just split this place into one subspace with some, chose some basis, and then all the remaining bases. This you can always do, right? Now let's do the following. So I can erase the top part here. So let's look at, by definition of invariant subalgebra, so what we are saying is that any of the y, any of the y with y, and we are saying this is abelian, right? Because we said this W is an abelian invariant subalgebra, which means that all the v's commute with each other. Right? So all the yi with yj equal to 0. This is because it's W is abelian. So I've used the fact that it's abelian. Furthermore, yi with xj, so x's are the remaining ones, right? Which are not inside the y, inside the W, they are in V. But we also are saying that W is an invariant subalgebra. Okay? So this is again contained, so this is contained in W. Okay. So which means it will be some linear combination. Okay. There will be some, I don't know, AI, BI, by I, where AI is some numbers. So this is because it's contained in W. And okay, Xi, Xj, we cannot say. Xi, Xj commutator can have, is just generally an element of the full V. So in principle, it can be a combination of Y and X. We cannot say anything about it. So it will be some combinations, I don't know, BI, YI plus CI, XI, no? In the appropriate range. I going from 1 to M, I going from M plus 1 to N. So it will be generally that. So this is the general structure. That is what we get from those definitions. Okay. So now let's look at the adjoint action. So if I look at the adjoint action of say y, any one of the y, I will yi. Well, that is now I can ask. I have chosen this basis, right? So I can think of this as a matrix. This guy is going to be a matrix. This adjoint y will be some matrix, which will be n cross n matrix. Right? So I'll choose this matrix. I'll choose this matrix in the following way. I will choose the matrix like so. The first m guys will be the y's, and the remaining guys will be x. And here, first y. So this is the n directions. This is the n minus n direction, n minus n. So this will be y, and this will be x. I will write this in the adjoint. This guy I can always write it as a matrix, right? N by n matrix. And that we can understand by just looking at how it acts. If it acts on a yj, it is 0. If it acts on x, xj, it's going to be again some combination of y. Because you see, this add is nothing else but the commutator. Yi with commutator yj is 0, and yi with xj is again some combinations of y's. Okay. But no x appears here. So if I write the add y as a matrix, actually I don't even have to write this, but let's write it as a matrix. So add y as a matrix, it is going to be, so what it does, it takes this to 0, right? So whatever the matrix is, it should take this to 0, and this guy to y, right? So how I want to write it as a block structure. So this is n minus n. This is n minus n. So how will you write it? Y with y is 0. This part is completely 0, right? Because remember, here is y, and here is x. So when this add y acts on the y's, it gives you. So suppose I have nothing here. I put everything 0 here. The answer should be 0 for arbitrary such entries. So this must be 0. Okay? And what about the action on x? When I apply on the x, when y acts on the x, it gives you back these elements only, right? So this is 0. That is not 0. That is something. Okay? That may not be 0. Correct? Because you see, when this matrix multiplies, what you're going to get this 0, but that goes up, right? Which means it is again the y directions. So this is the structure of y. And what about the add x? So add x. If x acts on the, so look at the add x. So we are saying add x acting on y is again some combination of y, and add x acting on x is going to be some combination of x and some combination of y in general. Okay. So add x will be given by, again in this matrix form. How will you write it? Let's see. So when it acts here, so let's say this components were 0. When it acts here, I'm going to get again some combination of y only, right? So this part is not 0. No? Is that clear, or am I making a mistake? When it acts here on the y, this gives you something which back in thing, and when it acts on the x, it should give you both in general, right? So it should, this could be non-zero, this could be non-zero, but this is 0. That's what we're saying, right? Yeah, because if this was not 0, add x acting on the y will give you something in the x, but that is not the case. That's not the invariance of algebra, right? Okay, so let's see what we get. So now let's look at the action of add y with add y. So apply two times the add y's. So some yi, yj in general, but generally y's. So it will be product of these two such matrices, right? But that's going to be 0 completely. You take these two matrices and multiply. If you take these two blocks, 0, something, 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 and multiply it again, it's exactly the same type. So this with that is 0. This with that is also 0 because this 0 multiplies there, right? And with this with anything is 0, so the whole thing is 0, 0. Now, what about add x? Add x with add y. Add x with add y. So I have to multiply this matrix to that matrix, or other way around. Add y to add x. So this times that gives you 0. So let's just do it. So what is the structure of this block matrix? So this block has to be 0, right? Because if I multiply this with that, it is 0. This with that is not 0 in general. So here it may not be 0. Okay? And this with everything is 0. So here it's 0, 0. But now the b is defined as, so how is the b defined? So this byy, byi, yj is basically a trace of this, right? That's how we define b. So trace of this is 0 clearly. Okay. And byi, xj is by definition trace of that, yi, xj. That is that. So trace of this is also 0. The diagonal is all 0. So the conclusion is, if I now write down the metric b, x with x will not be 0. If I look at add x, if I take the product of add x with add x, then there are diagonal terms. So b of xi, xj is not 0. That's not 0. But what is important is that all these guys are 0. Okay? So now let's write down all the b's. B in this basis. So if I write the b as a matrix, B as a matrix, again in the same basis. So here is y, so in this block form, x, x. So we are saying b with y is 0, okay? Y with x is 0. This is symmetric, so bx with y is also 0, okay? Here there is something non-zero, but determinant of this is 0 then, right? So it shows that, so if there is an abelian invariance of algebra, the determinant is 0. So this is the structure. So this is one way of, the only one of if and only if there is only one has been proven. Other thing is more complicated. To prove that if there is no invariance of algebra, abelian invariance of algebra, the B is invertible. The determinant of B is not 0. That is the more difficult. Okay, this is one thing. And now finally, just the last bit. Yeah, this is again another thing here. This is again is an important thing. I think I can erase here. The last theorem, which again we will not prove. So that theorem is 12.2, theorem 12.2. It says that a semi-simple algebra is a direct sum, that's important thing, of simple algebras. So a semi-simple, from this previous theorem, it says that it shall have no abelian invariant subalgebra. But of course it can have non-abelian invariant subalgebra, there's no problem with that. It's only abelian invariant subalgebra should not be there. So what happens is that, so if you consider a semi-simple algebra which has an invariant non-abelian subalgebra, then that invariant non-abelian, so you can decompose it as direct sum. So in this, suppose this W was not abelian, non-abelian, was non-abelian. So W is in V, is a non-abelian invariant subalgebra. Invariant subalgebra V. Okay. Then there is no problem. I mean, it can have. It can have non-zero determinants. So it can be semi-simple. Of course, I mean you have to make sure. Maybe you find a W, which is a non-abelian invariant subalgebra. But maybe W again contains something else. I don't know. Let's say U. Okay. Which is an invariant subalgebra of W, and that happens to be abelian. Okay, then it is not semi-simple. So the statement is that there is no, so we are already assuming that it has no abelian invariant subalgebra. Okay, the only invariant subalgebras are non-abelian. Okay, so it is this situation. Then what happens is that you can redefine, you can find so W is, say, this m-dimensional, and there is n-dimensional. So you can split this n into m-dimensional and an n minus n-dimensional spaces, such that, so this m-dimensional space is the W, generated by W's. Then from the remaining guys, I can find combinations such that these two commute with each other. Okay, that is the thing about direct sum. Direct sums, if I have a direct sum of algebra V1 with algebra V2, the generators of V1 and V2 commute, right? So what I'm saying is that this V can be split into W plus direct sum with something else, I don't know, W prime. The W prime is n minus n dimension. And the way the Cartan killing form enters there in this decomposition is that what I was calling this Y, generators were Y, and we were calling generators here Y and generators there X, no? X were not necessarily commuting with Y. Right? X were, the only relation was that X with Y gives you back Y. But what I'm saying is that if it's a semi-simple algebra, you have a non-degenerate metric, then you can choose a new X prime, let's say, which is a combination of X's and Y's. Okay? In such a way that those X primes commute with the Y. Okay? But again, we will not prove that, but because again, that requires a lot of other information to prove that statement. But this is the statement that any semi-simple algebra, if you have some situation like this, you can redefine your combinations in such a way that you can write it as a direct sums of algebras. Each one, they will be simple. So you keep splitting. So if you start with a semi-simple, you decompose in terms of, let's say, W and W prime. Okay. Maybe each one of them has again invariant subalgebras, which are non-abelian. Then you decompose further, so W1, W1 prime, W2. This may also have invariant subalgebras, W2 and W2 prime, etc. No, but finally, if you are talking about a finite dimensional algebra, this process has to stop somewhere. Okay, and finally, when it stops, it's going to be simple algebras. So each one of them will be simple algebras. So this is the basic idea that any semi-simple algebra can be written as direct sums of simple algebras. So conclusion is that if you are interested in semi-simple algebras, it is enough to study simple algebras. Because if you know everything about simple algebras, for direct sums it's immediately, you can deduce everything about the direct sums immediately. So from now on we'll be focusing on, okay, not immediately. Yeah, from now on essentially we'll be focusing on simple algebras. So I think I'll stop here, and from tomorrow onward we will do this chapter. More detail. So any questions here? Was one of the lectures missing in the video?
Yes.
Huh?
Yes.
15. 15 was missing. How come? I thought I pressed it. I must have forgotten to press that. Or maybe I didn't press it properly enough. There's just one thing, one small comment. Oh, I should. Did I? No, it's still on. An example, I mean, you can ask the question, remember we discussed the Euclidean algebra of the rotations and translations, no?
Yes.
So try to think about it, and tomorrow we can try to think whether that is a semi-simple algebra or not. It has an invariant subalgebra, remember? Well, actually, we already know. Invariant subalgebra was a translation, which was abelian. So it is not. Sorry, so you don't have to think about it. It's not a semi-simple algebra. Because also we know that algebra you cannot write as a direct sum. It was a semi-direct sum also. Right? But yeah.
Yes, because there's a rotation and
Translation. Yeah. Okay, so you don't have to think about it. Okay, so.
Professor, I have a question.
Yeah, go ahead. Yeah.
So we said that we can write V as a direct sum of W and W prime. So
Yeah.
I just wanted to recap the definition of direct sum. So by definition, direct sum means that if we take two elements from W and take the commutator between them, we will get back another element from W, and same goes for W prime. And we do not think about the commutators between one element from W and another one from W prime, right?
Yeah, it gives you 0. I mean, if you take one element from, say W and another one from W prime, then they commute. They mutually commute.
Okay, so in matrix form, it's just a block diagonal.
Yes.
It's just a block diagonal form, and the off diagonal parts is 0.
That's right. Yeah, I mean, roughly, you see, intuitively one can see that. We said that when we started with this decomposition, we had this we were calling X and Y. This we were calling Y, and the remaining guys we were calling X. We said Y with, okay, this is not abelian, so Y with Y is again in Y, no? Because that's a subalgebra. And then X with Y, in general, is also in Y, because that's invariant subalgebra. But X with X could be X and Y, right? Some combinations of X and combinations of Y. But what we want is that we want to remove this guy, no? We want to remove this thing from the right, to write it as a direct sum. No, we want to remove this. We want to remove this so that so I want to modify this. I want to modify. In fact, we need to do two things. So I want to modify X to some X prime, where X prime will be a combination of X and Y. I mean, some suitable combinations. In such a way that we want X prime with Y equal to 0, and X prime with X prime is only in X prime. is again combinations of x prime. No? Now that you could try to do if you have, I mean, so you want to find some combinations, right? So x prime will be x plus some combination y. xy gives you y. xy gives you y. Yeah, xy gives you y, and yy also gives you y. Right? So if you write x prime, which is x plus y, the first term xy gives you some combination of y. Y with y also gives you some combination of y. Right? But the question is, can we find some combinations here? No? And that combination is actually found by using this Cartan-Killing forms, you know, the metric, and adding. So these coefficients that we put here, these coefficients involve the metrics or inverse metric and things like that, and which can be done by if its determinant is not zero. Right, but it's still complicated. I'm just giving you some idea how this procedure is carried out. That it turns out that you can find combinations such that the terms that you get from here, x, y commutator, these combinations and these combinations, they cancel. No? You can find these combinations here. And finally here, okay, it becomes a bit more complicated. But yeah, I'm not sure. Maybe if you satisfy this, probably this becomes automatic. Probably this becomes automatic. But it crucially uses the fact that the metric is, you can invert the metric.
Can a metric be non-invertible? Can we have
Can it be?
Non-invertible? Can the determinant of any matrix be equal to 0?
Oh yeah. I mean, abelian algebras, for example. Take an abelian algebra, all the, adjoint action is 0 identity, right? So you have a 0 matrix times 0 matrix, trace of that's still 0, yeah. So any abelian thing is 0, yeah. Or take the more non-trivial thing, this Poincare algebra, Euclidean algebra, which has an invariant abelian subalgebra, right? So even though the rotational part is non-abelian, but this theorem tells you that determinant of B is 0 for that. Okay, so any more questions? Okay, otherwise we meet tomorrow.